2014 was a very big year for me, both personally and in my career. My husband named it the year of the 3 Ps. And my slides aren't coming up yet. There they are. My husband named it the year of the 3 Ps. I became professor of radio engineering at the University of Manchester. I got pregnant and I presented the Royal Institution Christmas lectures. And all 3 of those things had a real profound effect on me as an engineer and a scientist. Now, as an engineer who studied astrophysics, I've always really enjoyed the practical side of radio astronomy. And I wanted to help solve one of the 14 World Engineering Grand Challenges. I wanted to engineer the tools for scientific discovery, and that's what I do. And I use radio waves and microwaves to do this. And this doesn't mean that I make microwave ovens, which I'm sure is what my friends still think I actually do now. What it means is that I use the radiation emitted in the radio and the microwave regions of the electromagnetic spectrum. Now, whether you're sitting at home, you're walking down the street, you're sitting here this evening, we are all bathing in a sea of electromagnetic waves. These undulating particles with no mass called photons that zip-zap invisibly through space at the speed of light. And so I work in the part you can see up here, the radio part, radios and microwaves, and those photons will have a certain amount of energy, and then as you go higher and higher into cosmic rays, you get higher and higher energy. And we live and move through this invisible broth that is all around us all the time. And over history, we've learned to use this invisible energy in air as a vehicle to transmit and to receive data. And that includes trying to improve our understanding of our knowledge of the universe. So that's my grand challenge. That's what I do. I engineer the tools for scientific discovery in radio astronomy. And here's a picture of one of the telescopes that I've had the privilege to work on in the past. This is the Lovell telescope out at Jodrell Bank Observatory in Cheshire, 76 meters in diameter, so it's a pretty big beast. And me and my team design instrumentation to receive the radio signals from space. And so we have, right in the center of that, you would have your front-end receiver. And that front-end receiver would have an input, so your signals coming in. Then it would have an amplifier here to amplify the signals. And then the signals get mixed down here just to a lower frequency so we can digitize that back end as well. And so your input wave is that nice looking sine wave. But of course, the input wave isn't as nice as that. What actually happens, if we could just switch to the overhead projector, please. What actually happens is you have a sine wave like this, but it's actually quite noisy. So you have sort of noise on it like this. And so if you look at that from a frequency point of view, if you look at the frequency and then the amplitude, you would have a noise floor down here, and then you'd have your signal here. You might have a few signals along here. And what you want is that noise floor here and the peak of your signal to be as high as possible. And this is your signal-to-noise ratio, so you want that to be as big as possible. So the more noise you introduce into your receiver, the higher that noise floor will go. So you can go sort of up here, and you can see if you start to increase that noise flow, the signal-to-noise ratio is reduced, and actually you start to lose some of your original signal as well. We could switch back, please. Thanks. So we want to make sure that the noise we introduce is very, very, very small. So we have our receiver right at the the front end of the telescope, and sometimes that's right in the middle of the dish, like it is with the Lovell, and sometimes it's behind the dish as well. So in that, you would have what's called a cryostat, just a big fridge, a big refrigerator, cooling that front end, cooling it to try and reduce the noise that you input. And right at the front end, you would have this low noise amplifier, and that would sit in that first little box there. And then, like I say, it would be digitized, down-converted and digitized afterwards. So in that little black box area is the LNA, the low noise amplifier, and that's the bit that we're interested in. So right in the center of that tiny little black thing there is the actual amplifier. Okay. Now, this low noise amplifier is one of the most important, if not the most important, component in a radio telescope. Now, the reason I'm sort of bigging up the low noise amplifier is because that's what we work on in my research team. And so inside that is something called a MMIC, a monolithic microwave integrated circuit. And that's basically our amplifier. So that's our transistors, our resistors, our capacitors, etc. But these are really, really small. So you can see this one it tells you right in the bottom right-hand corner, it's 2 by 2.5 millimeters. This is actually quite a big MMIC in a way. And so this is what me and my team do. So MMICs are dimensionally quite small, and MMICs are used quite a lot. We have them in our cell phones and our smartphones. But these are some designs from my team. And we can't use the type that are in cell phones and smartphones because they have to be virtually noiseless, so we don't increase this signal-to-noise problem. And they have to be cryogenically cooled, so they're cooled to around minus 260 degrees Celsius. And so we design these, we use lots of different types of semiconductor materials in order to design them. And the work on our LNAs is for ground-based and space-based telescopes. And the very first telescope I worked on was a space project, and it was called Planck. It was a space mission designed to look at the remnants of something called the Big Bang. So everyone know the Big Bang? Not the television series? Yeah. So 13.8 billion years ago, there was an event, the Big Bang. And Planck was this international collaboration between the European Space Agency, ESA, and NASA. And many, many engineers and scientists from around the world working on this amazing project. It was a radio frequency, an RF instrument, designed to look at this naturally occurring radiation that you see in the radio spectrum. Now, 13.8 billion years ago, the universe was filled with a hot, dense soup of protons, electrons, and photons. And when these protons and electrons joined, they formed hydrogen, and light was set free. And that light over time has been stretched into the microwave wavelengths. And that's why we call it the cosmic microwave background, or the CMB. And effectively, it's a snapshot of the oldest light imprinted on our skies when the universe was just a few 100,000 years old. And so Planck was designed to look at this instrument, at this phenomena. And its objective was to analyze the CMB in a way that had never been analyzed before. So the highest accuracy ever. And so this remnants of the Big Bang, the reason that we try and take this out into space is to try and reduce that noise that we'd have if we try and observe it on the Earth. And so what you see there now is a picture of the Planck. The Planck actually rotated like this in order to observe the cosmic microwave background. And so it mapped this cosmic microwave background, the CMB. And here is an early map of it. So you can see it's a color map where the changes in color represent tiny changes in temperature. And these tiny fluctuations in temperature correspond to changes in the density of the universe, which represent the seeds of all life as we know it, structure as we know it now, so the stars and the galaxies that we have today. So we need to have very, very accurate maps of the cosmic microwave background so we can understand both where we've come from and where we're going to in terms of the universe. So Planck was launched, and it was sent out to a place called L2, Lagrange point 2, which is 1.5 million kilometers further away from the sun than we are here on Earth. And it mapped the cosmic microwave background. It mapped the CMB. And this is what the map looked like after 15 months of data being collected. So you can see it's much, much higher accuracy, much more resolution in that map. So it allows us to understand the composition of the universe from its birth until the present day with a much, much higher accuracy. And the amount of data that you have to generate in 15 months is enormous, absolutely enormous. And I remember showing this Planck spacecraft to some school children years ago. And that sort of brilliant question time that you get, that you can only get with children. And one of the questions from the children was, what does the cosmic microwave background sound like? I was like, what a great question. I have no idea what it sounds like. And it sort of stuck with me for such a long time. And then when I started my first lectureship in the University of Manchester, I was talking to a professor of digital signal processing, Professor Gaidecki, and I was telling him this story. I was like, oh, have you got any data? I was like, yeah, I'm pretty sure we can find some data. And he was like, oh, well, give it to me and I'll try and reduce it into the audio. I was like, okay. So here's what it sounds like. So hopefully we got some sound here. So I played it twice there, but that's what the sound of the CMB is. And I wish I could find that child now to tell her what it is like now. And that there was huge amounts of data just to get it. I actually played it twice, just so you could hear it. The amount of data it took just to get those first few seconds of it was enormous. And data is such an important commodity for us these days. It's being mined like coal. It's refined like crude oil. It's stored in high vaults like gold, and it's sold like rolled steel. Every 2 days now, we create as much information as we did from the dawn of man up until the year 2003. And that's something like 5 exabytes of data. That's according to Eric Schmidt of Google fame. So let me just repeat that. In the past 2 days, we have created as much information as we did from the dawn of civilization up until the year 2003. Huge amounts of data. But what is data and information? Well, at the fundamental level, all data is digital, consisting of a series of ones and zeros. So we can represent any physical system. But this information content must, expressed in bits, must be limited. It has to be limited. And this is known as the Bekenstein bound. So in other words, if a system's mass, energy, and dimensions are known, the Bekenstein bound defines that we can recreate, knowing the maximum number of bits, we can recreate a system perfectly, right down to the quantum level. So if that's true, can we represent the total information content of the human brain? And of course, the answer is yes. Of course we can. But it's a big, big number. Very big. But it's limited. It's still a limited number. So the total content of the human brain in bits is a very, very big number. It's around 2.6 times 10 to the 42 bits. So in other words, if you could download the information content of your brain as a song and play that song, it would last for 50,000 trillion years. So better be a good song. We're now using data and connecting instruments that will have a profound effect on the way we fly, the way we farm, the way we design cities, and so much more. And I believe it will play an underpinning role in helping us to solve some of these world engineering grand challenges that we all face, including engineering the tools for scientific discovery. And it's amazing how much technology you can actually overlap in these things. Smart machines for astrophysics to smart machines for farming as well. For instance, more than 2.8 billion people are still affected by water scarcity. And that number will only increase as the need to feed a growing population also increases. Now, there are several projects, including one in our research team, that are using subsidized sensing technology and wireless systems to help farmers measure and monitor subsoil parameters, so soil temperature, moisture, and nutritional information needed for crop growth. So this system that you see here integrates radio frequency identification, RFID, technology, and this subsoil sensing technology. So RFID technology is almost ubiquitous these days. We see it everywhere. Sometimes you see it on clothing or in foods in the supermarkets. Same sort of technology here. And then what we have in those nodes is we have the sensors that are going to sense in the soil, and then our RFID tag in there. And all of these nodes are then buried in the soil. But they can't contain any batteries, because the last thing we'd want is the battery acid to go into the soil and contaminate the soil. So those nodes sitting in the soil have to be able to harvest their energy from the electromagnetic reader that's sitting on the front of that tractor. So what happens is the nodes are all buried in the soil, and then the farmer will come along in the tractor, and it will read wirelessly through the soil the information in each of those nodes. And that's helping the farmers move towards this model of precision agriculture, so just using water where it's needed. So we're saving this precious resource, we're saving this water by just using it in parts of the field where it's needed. Now consider aeroplanes, jet engines, gas industrial turbine engines. Aeroplanes are mission-critical vehicles, and as such, we want them to be safe and reliable. So during their development, thousands of sensors are put inside an engine. So they're equipped with so many of these, and they're all hardwired into a data acquisition unit which sits in the engine during its development. And these hard wires are expensive, they're inflexible, they are susceptible to cable and connector faults as well. So what we want to do is try and remove all of those wires, and you're talking like kilometers worth of wires inside one of these things, and replace it with a wireless sensor network. Now imagine, so the wireless sensor networks may be the size of a cell phone, and imagine if you don't need a really, really skilled person now on that jet engine. They can just walk up, put these wherever they want on this engine, and once these nodes are in there, they start talking to each other, they start building up a picture of what that engine is doing. So it's measuring the force, the acceleration, the temperature during the development of this engine. Now what you can do is then design the future engine to be much more efficient, so you can reduce, hopefully, carbon emissions in the future. And for me, this is really important as part of our research, that we are potentially helping with multiple engineering grand challenges. We're trying to save precious resource using radio technology. We are trying to reduce carbon emissions using radio technology. And quantum computing is another example of that. A researcher in our team is trying to look at low noise amplifiers, the LNAs that we use in radio astronomy, to improve quantum computers as well, to work with quantum computers. But of course, my passion still lies in radio astronomy, so the engineering in radio astronomy. And those instruments in radio astronomy are now big scale, big data instruments. Now, we've been broadcasting radio waves and listening to signals from space for over a century now. And that's allowed us to understand how much of the universe there is beyond what we think we know. So these days, telescopes are being designed to look deeper and deeper into space. And my team is very fortunate to work on 2 of these incredible projects, truly incredible projects. They're groundbreaking. The first is working with hundreds of engineers to build the largest science facility ever built by mankind. And it will probe deep into the universe. What will they find? The unknown. It's called the Square Kilometre Array, or the SKA. It actually has their headquarters out at where Jodrell Bank sits in Cheshire, but it's an international project, truly international. It will sit in Western Australia and in a remote area in South Africa. And the total collecting area of all of the dishes and the dipoles will make up 1 square kilometre's worth of collecting area, hence the name. And it's currently being built now. The size of it will make it 50 times more sensitive than any other radio instrument ever. And that will address key and ambitious questions in cosmology, astrophysics, and fundamental physics. In fact, the SKA will be so sensitive, it will be able to detect an airport radar-like signal on a planet 10 light years away. Super sensitive. And as you can see from the diagram here, it's currently made up of 2 different frequencies which make up 2 different types of antenna design. So the low frequency is that top picture you can see there, the sort of more dipole aerial type antennas. And they'll sit out in Western Australia. Excuse me. And they will work from about 50 megahertz up to about 350 megahertz. But just look, these have spectacular parameters. Both of these projects, they have spectacular parameters about them. And it's really turning on its head how we design instrumentation for radio astronomy. Gone are the days where you might just have 1 dish. Look at this one. There's 130,000 of them for this low frequency. There's over 200 dishes sitting in South Africa. And this is just phase 1. This is what they want to do in phase 1. By the mid-2020s, it's hoped to have millions of these low-frequency dipoles sitting in Australia and thousands of dishes spread over the area in South Africa. And look at the amount of data, even just this phase 1 is showing 35,000 DVDs every second from those dipoles, from those low frequencies, every single second. The equivalent of 340,000 computers, laptops from those dishes every single day. Huge amounts of data. Now, it's estimated that the low-frequency antennas alone will generate more than 5 times the global internet traffic. Just this one experiment is going to produce more than 5 times the global internet traffic. So if we could express the data that the SKA will collect in 1 day as a song and download it, it would last for more than 2 million years. This high-performance computing that they're going to need will need to perform 10 to the 15 operations per second. Transfers of 1 terabyte images will be needed every single minute around the world. This indeed will be a smart machine measuring the universe. And in a way, it's already started. This is the site, you just saw a flyover of what it might look like when it's all built. This is the site as it sits now in Western Australia, and it has another small experiment on it, much, much smaller than the SKA is going to be. And it sits at around 78 megahertz, so sort of the FM radio signal range. And they detected a very, very weak signal using this antenna. And they think the detection would have been pretty much impossible from anywhere else, a ground-based site in the world, because of all the RFI, the radio frequency interference that we have around the world. This is why this site is so very special. They're able to do such low-frequency work still. Now, this was part of an experiment called the Global Epoch of Reionization Signature, or EDGES. And basically, what it found was, after the Big Bang, the universe cooled and went dark for a few million years. And in that darkness area that you see there, gravity pulled that matter together and started to form things, started to burst into life. So stars were formed at that point. And it brought together something called the cosmic dawn, which is a very specific area in our universe's history. What this experiment did was really redefine this artist's impression and redefine the timeline of the universe, because it showed that those first stars did actually emerge 180 million years after that Big Bang. So that detection from that signal, that one signal that they found, were the first steps in understanding where stars have emerged. And that was 180 million years after the Big Bang. And I think this is a really powerful demonstration of what can be achieved with a combination of a very, very good site, which the SKA is going to be on, and world-class engineering. And I think it's boding very well for the great discoveries that I think the SKA will make. And the early impact of the SKA is also true with the dishes. The data that's collected from these early phases of the SKA is already having an impact in making new discoveries. They're still in the early phases of this, the commissioning phases of phase 1. But in South Africa, they have a precursor to the SKA called Meerkat. Good name for the South Africans. And it's a radio interferometer being built by the SKA team. Now, they observed something called a magnetar, and they observed this during the commissioning phase of some of these dishes. So the whole thing's not built yet, but just a few of these dishes, they observed something called a magnetar. Now, this magnetar awoke in 2017 from a 3-year slumber, and they were ready to catch this. So when the stars reach the end of their main sequence, they undergo a gravitational collapse and they eject the outermost layers in a supernova explosion. And then what's left is this sort of dense spinning core, which is made up of neutrons, and hence you call it a neutron star. And there are not many of those in our galaxy, in our Milky Way. And an even rarer subset of those are magnetars, which are these highly magnetic stars, the most magnetic things in the universe. And there's not very many of them at all in our galaxy. And so Meerkat, or the precursor, was able to detect this magnetar. So what they did was they told NASA about it. NASA then took its X-ray telescope that's orbiting the Earth, and it observed the magnetar. And so they've got some great information, great data about this magnetar that had been awoken from a 3-year slumber. And they started that with this precursor to the SKA. And that's it, sort of, the SKA is a lower frequency, so it goes up to around possibly 20-ish gigahertz. And at the other end of the radio spectrum is the other project that we are privileged to work on, called ALMA, the Atacama Large Millimeter Array. And it is revolutionary in its scientific concept, but also in its engineering design. Now, this is in Chile. There are 66 dishes in Chile, 5,000 meters above sea level. And it's looking sort of millimeter to sub-millimeter wavelengths, so it's into the sort of hundreds of gigahertz and then sort of sub-terahertz regions in the frequency bands. Now, this is so sensitive, it really will open an entirely new window on the universe and allow scientists to unravel those long-standing and important questions and important astronomical mysteries. And this is already operational. This isn't futuristic. This is happening now. And this is something that ALMA observed a couple of years ago. Sort of on the left, you can see there is an early picture of this. This is actually a star which had a sort of slightly lower mass than our sun. And you can see what the observations looked like in 2011 before we had ALMA. And then on the right, you can see a very, very different picture. Now, much more resolution, much more data has been captured. And what they found is this low-mass star has planet-forming disks that you can see around that star. So you can really start to look in much, much more detail about some of the things that you've observed in the past, but you can see it in much, much more clarity as well. Now, this video shows what ALMA is doing now. So the dishes we're moving around there were ALMA. So what you see here, we start with sort of quite a broad view of the southern sky. ALMA is in Chile, so we're observing in the southern sky. And it starts to zoom in on quite a faint constellation, and it's nicknamed the Clock, this faint constellation here. And when we get closer, we can start to see quite a striking spiral galaxy in there, and that galaxy is known as NGC 1433. It's a snappy, off-the-tongue sort of name. And the central part of the galaxy that you can see there, it hosts a supernova black hole right in the center of it. And observations of the surroundings of that supernova black hole have revealed, using ALMA, and you can only do this with ALMA, have revealed both a sort of a spiral structure that you can see there to the molecular gas that's surrounding the black hole, as well as this newly discovered outflow of material. And like I say, no one has ever seen this without ALMA. It's truly revolutionary as a science instrument. But first, it's revolutionary in its engineering design. The surfaces of these dishes are almost perfect, with none of them deviating from a perfect parabola by more than 20 millionths of a meter. This prevents any of the incoming radio signals to be lost, so that the resulting picture you get is a much more complete picture of that distant cosmic light that you're trying to observe. And there's so many more amazing engineering challenges with ALMA. This is how ALMA works. The incoming signals come in, and then they are gathered together and then put into the receiver. So you can see it's the back of this dish that holds the front end of that receiver where the red dot is. And that's where the low noise amplifier will sit inside its big fridge inside this cryostat as well. And that's the part that we are working on. And then the back end gets digitized, and all of the dishes, all the information from the dishes gets put together, it gets correlated and put in this correlator as well. And there's lots of numbers that make up ALMA. There is one supercomputer operating at the highest altitude in the world. It has 10 times more detail than the Hubble Space Telescope images. 17 peta operations, or 17 trillion operations per second are needed. That makes it the fastest computer on any astronomical site, and it's equivalent to billions of dollars worth of personal computers that are needed to make those necessary calculations. In that correlator, there are 20 million welding points. 40 degrees is the difference between the maximum day and the maximum night temperatures in Celsius. And you have to make that instrument work exactly the same no matter what that temperature is. And they have 10 receiver bands. And we design the low noise amplifiers, the LNAs, and inside that cryostat again. And as I say, there are 10 receiver bands. And so ALMA currently works from 35 gigahertz up until just below a terahertz, 950 gigahertz. But if you could cover more bands, more frequency bands, you can cover more signs. So more signs can be explored. So what we're trying to do is trying to combine two of those bands. So combine band 2 and band 3. So to go from 65 gigahertz up to 116 gigahertz. And you may say, well, that sounds all right. What's wrong with that? It's really, really difficult to do. It's 65 gigahertz to 116 gigahertz bandwidth is enormous, I assure you. And ask my researchers how hard it is to do. It's a huge bandwidth. But if we can do it, it means the scientists can observe more of the universe. And so we want to do it. So if we can fit more engineering into the receiver, the scientists will get more out of their telescope. So that's what we've done. We've tried to combine those two bands, band 2 and band 3, and make it the lowest noise possible. Now remember, we've got to keep these as low as possible. So we can't introduce any more noise, definitely don't want to, and they have to be cryogenically cooled as well. So we are producing these MMICs, these monolithic microwave integrated circuits, and we are cooling them. And this is the result. So you can see the frequency from 67 up to 116. There's a number of different low noise amplifiers that you can see there. And the dotted lines that you see going across were actually the specifications that were given from the ALMA project as well. So you can see we're sort of exceeding all of those because the noise temperature, which is written in Kelvin, absolute temperature, on the y-axis, you want that to be as low as possible. So it's been demonstrated that these low noise amplifiers have set a new record in broadband noise at these frequencies in this band. There is nothing better than these in the world right now. We are pushing the very boundaries of semiconductor technology in these bands. And results like this are why scientists can push their own boundaries as well, and why we are solving one of the 14 world engineering grand challenges. We are truly engineering the tools for scientific discovery. And I get really excited about this plot, but I'm so disappointed with myself as well, because this represents years worth of work. For one particular PhD student, he was a PhD student at the time, it represents his entire PhD, at least 3 years worth of work. And I should be using it to infuse the next generation of scientists and engineers, showing them that, what can they do? And, how can they engineer their own tools for scientific discovery? And what have I reduced it to today to show you this evening? A 2-dimensional plot. Great. Surely I could have done better with this. I definitely need to improve on this. So I think the only thing I could do right now is to applaud my research team who are here this evening. So I'd quite like you to stand up, research team, where you are. There you are. Please stand up. The work that these guys do are truly, truly inspiring. They certainly inspire me, and I think they really do inspire that next generation as well. And it's so important that we do inspire that next generation, which sort of brings me back to where I started, to the other P's. As I said, I was made professor, fabulous into my research. Then I had the huge honor of presenting the Royal Institution Christmas lectures. And I can't quite explain how much of an effect that has had on me as personally and in my career as well. It's truly, truly life-changing. And I don't think you can say that about many things in your life. Then, as it was announced that I was going to present the lectures, I found out I was pregnant. And I was like, yes, that's great. And then I started to do the maths, and I was like, ooh, I'm going to be very pregnant. And I was like, oh man, why do these two amazing things have to happen at the same time? I'm going to have to say to the RI that I can't do the lectures. I will have missed my chance. Really grumpy about it. And my husband was like, why can't you do it? I was like, oh, I don't know. Why can't I do it? No, maybe I can do it. And so I did. And Elizabeth helped me give those Royal Institution Christmas lectures, and I was 8.5 months pregnant when I did it. Thankfully, Elizabeth stayed where she was supposed to stay, and the lectures were about technology and not about biology. And it was truly amazing experience. I mean, truly, I can't, like I said, I can't think of many things that have such a profound impact on my life. And And I found it amazing to be able to connect my passion for engineering and science with that next generation as well. And we did some amazing projects as part of the Christmas lectures, some 3 grand challenges. The final grand challenge was to create this Robot Orchestra. And it was great to show how creative STEM subjects are. Science, technology, engineering, and maths are. And so what we wanted to do for this last grand challenge as part of the Christmas lectures was try and look at recycled, repurposed instruments, create music from these recycled, repurposed machines that you might find lying around your home. And it's amazing what you can find lying around people's home as well. You could see right in the foreground there, that's a dot matrix printer. I mean, I think I'm talking to an audience who remembers dot matrix printers. And the music it made was beautiful. Right at the back, just behind my head there, you can see some sort of big pipes. That was an old vacuum cleaner organ. So a guy had made a beautiful old vacuum cleaner into this organ. And what it showed, these were some fabulous engineers and tinkerers from around the country all came together to create this Robot Orchestra. And what you see in front of you here is an example of one of them as well. And again, I am talking to people who remember these. Floppy drives, yep. It's not always the case. Even my first years at university now are like, oh, that's so retro. I'm like, thanks. But what you see here is floppy drives. And so we were thinking, okay, if you can make a dot matrix printer or an old vacuum cleaner create music, surely we can get some floppy drives to create music as well. And so that's what we did. So you see before you 16 floppy drives here. And what you hear is the motor. So when you sort of put your floppy drive into, put your floppy into the drive, you had that sort of motor that fed it in or ejected it. And that's what you're going to hear. Those motors are moving. Then you have this sort of electronic brain sitting at the heart of it all here. And that created musical, digital interface music, MIDI files. And so any pretty much music, we can create a MIDI file, an electronic sheet music effectively, for these 16 floppies. So I'd like to play some music for you from this tonight. See if you can guess what they are. Eye of the Tiger, so the Rocky theme tune. Okay, I'll give you another one. Everyone must have got that one. Star Wars, that was? Right, okay, see if you know this one. I played that one so we use that as part of the much bigger orchestra when we're talking to children about how great and how creative engineering is. And I played that one, and I was like, right, okay, the whole orchestra is going to play this piece of music. And so I played the original, Hall of the Mountain King. And I was like, so what is it? And one of the first times we did it, this arm went up like really quick, just like, me. I was like, okay, what is it? And she went, it's the Alton Towers theme tune. I'm like, well, yes, you're not wrong. It's Hall of the Mountain King as well. So So, repurposing these, showing how creative science and engineering is, and hopefully inspiring that next generation. We hopefully did that with the Christmas lectures, and we continue to do this as well. And this idea of this robot orchestra that we started from the Christmas lectures has just gone from strength to strength. It seems to appeal to so many people, whether that's researchers at university, engineers, general tinkerers who have the most amazing garages you've ever seen, people in industry. If you ever want an industrial machine drive to play God Save the Queen, go to Siemens. They are the people to do that for you. And it really sort of brought all these different people together. The Women's Institute, the Manchester Transport Network, everybody wanted to donate things to us into the Robot Orchestra. And like I say, it's still going today. And we did this thing on the radio with Radio 6, Radio 1, BBC, that could a robot replace Ed Sheeran? And so we had a sort of a humanoid robot dressed up as Ed Sheeran, and all of our instruments were sort of the backing. You'd be pleased or not pleased, depending on your view of Ed Sheeran, that we couldn't replace Ed Sheeran with that. But what it does, hopefully, is captures the imagination of that next generation. And even today, excuse me, even this morning, I was talking to some children in Korea on a video conference with them. And they were talking about their own robot orchestra, making their own robot orchestra after seeing the Christmas lectures. And I was talking about how you can do that, how you can tinker and how you can play with things, and how that is just one step away from solving the great engineering grand challenges of the world, these 14 engineering grand challenges, and how they can engineer their own tools for scientific discovery as well. I asked a daughter of a friend of mine quite a while ago. I was sort of chatting to her, and she was like, "Oh, what are you doing?" And I was telling her, and she was saying, "Oh, it sounds really good. I think, maybe I'm quite interested. I've never been interested in before. Maybe, I quite like engineering and science." And I was like, "Oh, that's really good." And I said, "Do you think it's important that that people who work in engineering and science come and talk to you and try and sort of inspire you with what we're working on and what the problems of the next generation may be, the challenges to work on?" And she's like, "Oh, yeah, for sure." And I was like, "Why is it important that we inspire your generation?" Here's what she said.
"I'm you in the future. So if you help me now, in the future, I can be better than you."
I'm you in the future. So if you help me now, in the future, I can be better than you. I was like, that's just fabulous, and that's what you want. You want the future to be better than you. And that goes everywhere from my own students and my own research team right down to Abigail Coates when she was a few years ago. We need smart machines built by smart machines, children as well. I feel very fortunate to work with such exciting projects and people as well. ALMA, the telescope that is revolutionizing how we look at the universe now. The SKA, the Square Kilometre Array, this telescope that is literally turning on its head how I, as a designer, would ever design instrumentation for radio astronomy ever again. Gone are the days where you just have these one dishes. We're talking potentially millions in the future. It's the largest science facility ever built by mankind. But the amount of data that is going to generate will be enormous, truly enormous. And we don't know how to solve those problems yet. That's why we need that next generation of smart machines to actually help solve those engineering grand challenges. This has been my ABC of smart machines, and it's been my privilege to talk to you this evening. Thank you very much.